Rockets have always been popular and inspires young students to explore the world of science and space. With that, the idea of water rocket has been introduced to school students to fulfill this objective. Question is, how does a water rocket be launched and fly? Water rockets mainly work with the principle of conservation of momentum. Air is pumped into the bottle to create a region of high pressure in the rocket. When the launcher is triggered, the higher internal air pressure in the rocket will push and eject water out from the bottle, which result in a downward momentum. Based on the principle of conservation of momentum, we know that an equal magnitude but opposite momentum will be produced. In the rocket's case, an upward momentum aka thrust will be generated, thus the water rocket can be launched. Now, how can we safely bring our water rocket back? During the deployment, a parachute is used to slow down the descending process and act as a safety feature. After the launch and when the water rocket begins to descend, the frictional force between air particles and the water rocket will help to open up the parachute. Once the parachute has opened, sufficient drag can be generated to slow down the landing. Impulsive force can also be decreased and reduce damage on the rocket upon landing. Other features such as fins or vertical stabilizers will help in stabilizing the rocket along the flight. In this experiment, we are investigating the relationship between volume of water and the flight duration of a water rocket. In order to verify our hypothesis, the higher the reading of volume of water, the lower the reading of time taken from launch to landing of the water rocket, we have designed and built a model of a water rocket. Our design mainly focuses on making the rocket light and to have the ability to fly high. In conjunction with that, choices of materials used and designs of our rocket are based on our main focus. In order to fulfill that, we shape our rocket's nose according to a tangent or guide design from laminated plastic sheet. The smooth sharp-pointed nose tip ensures our rocket to have high penetrating power through the air particles during the ascent. During the descent, the cone surface of the nose helps in producing about 30% of drag to help slowing down the descent. While for the fins, we built it from straw boards according to the design of a clip delta fin. This design has a good aerodynamic and is suitable for low drag rocket as there are lesser surface exposed to the air, and it should thus able to play its part in stabilizing our rocket. In the meantime, straw board is light in weight and is crash proof. Since parachute helps to create drag, we needed a larger surface area. Therefore, our parachute was designed into a circular shape and has double the size of our rocket. A lightweight rubbish bag was used as it is waterproof. Nylon filament strings were used and tied to the parachute according to a reefing parachute design. This design ensures the parachute do not inflate too rapidly, which can result in extreme shock, and to create more drag. Nylon filament strings are capable to create enough tension to hold parachute tightly. As for our rocket's fuselage, we chose to use a thin and long bottle that is helpful to reduce frictional force acting on our rocket during the ascent. Our bottle's surface is also smooth and has no groove for the same reason. Once everything is put together, our rocket is ready to be launched. We first conduct a simple parachute test under both wind and without wind condition. This is important for us to verify the tensile strength of the parachute string. From the test, we managed to observe our parachute condition where there was no any tear or breaking of parachute string even under windy condition. When everything is secure, we can now begin the experiment. In order to study the relationship of volume of water and the flight duration of our water rocket, we begin by manipulating the volume of water. The flight time was observed and recorded. During the launch, we encountered a few successful and unsuccessful launch. Errors was detailed to generate solution for the unsuccessful launch. Precaution steps were also taken to reduce errors while conducting the experiment. Data collected was recorded and displayed in the table. The data was further interpreted into graph for the better understanding. Based on our findings, we concluded that our hypothesis is accepted. The higher the reading of the volume of water, the lower the reading of time taken from launch to landing of water rocket. That's all from us. Thank you and bye-bye.